Okay, in this lesson we're going to talk about absolute value functions, and we're also going to talk about piecewise functions a bit. So before we do that, let's do a quick review of the equation of a line in standard form. Alright, so see if you can remember this. What is the equation of a line in standard form? ax plus by equals c. The variables are both on the same side of the equation. What is the equation of a line in point-slope form? Okay, remember you need a point and you need a slope. And it looks like this. Y minus y1 is equal to m times x minus x1. And then what is the equation of a line in slope-intercept form? It's the most familiar form, y equals mx plus b. So this is a quick reminder of lines, linear functions, and now we're going to move on and talk about absolute value functions. Alright, a function of this form where m is not equal to 0. If we look at if m was 0, then this would become f of x is equal to 0 times x plus b plus c, and then we would just have f of x is equal to the absolute value of b plus c. Notice this doesn't depend on x, and so that's a problem. So we don't want m to be 0 because then this would not be an absolute value function. Okay, so this is standard form for an absolute value function. It has the absolute value signs there. You can see that. An absolute value function looks like a V, and here's an example of it. Okay, so the reason why it looks like a V is because you have these x values that you plug into your equation, and if the x is in the absolute value, when x is a positive number, so let's say this was when x is on the positive side, the stuff inside the absolute value, if it's positive, then the graph just kind of works like a line. And it's a line that would look like this. But as the stuff inside the absolute value gets negative, the absolute value takes those points and makes them positive in the y direction. And so instead of a line that looks like this, it gets moved up here. And that's why we have a V. Here's another absolute value function. This is one that when it's going down, this is if you had a negative value outside the absolute value. So an example of this would be if you had a negative sign out here, then it would just be flipped. All the values would look like that. And then here's another example. So an absolute value function is a V. It's always a V. This is the shape of an absolute value function. So if you see a function that looks like this, it has an absolute value sign, and the x is going to be inside the absolute value sign. The things that make it go up or down or more wide, that's what we're going to study next. Okay, an absolute value function always has a vertex. A vertex is the starting point. It's this thing. It's the middle of the V. And the vertex of an absolute value function is always either the maximum value of the function or the minimum value on the graph. Okay, so it's always either the maximum or the minimum. Here it's the maximum, all other values are lower. Here it's the minimum, all other values in that function are higher. All of their solutions to this absolute value function. The vertex is located here at negative b over m comma c from these values. So you can always find the vertex pretty easily. Okay, so let's go ahead and do an example. Let's graph this absolute value function. Step 1 of graphing an absolute value function is to find the vertex. That's always where you want to start. You want to start with the vertex. So let's find the vertex. How do you find the vertex? The vertex is at the point negative b over m comma c. So go ahead and find that. Okay, you might be asking the question, where do I get the values for b, m, and c to plug in here? The answer to that question is, if you remember that the standard form for an absolute value function is mx plus b plus c, then you can find those values now. Okay, so the m value is 3. The b value is 12. What is the c value? Well, in this case, there's nothing out here after the absolute value signs, so c is 0. There isn't a c value, or there is a c value. The value of c is 0. So the vertex is at the point negative b over m comma c, which is negative 12 over 3 comma 0, which simplifies to negative 4 comma 0, and this is that point plotted on the graph. Okay, so now that we're done with step 1, we're going to look at step 2. We want to find a point on either side of the vertex. We're going to pick an x value and plug it in and figure out what the y value is. So let's go ahead and do that now. I'm going to pick an x value that's on this side of the vertex and an x value on this side of the vertex, and I'm going to solve it. Let's pick an easy one. An easy x value on this side of the vertex is right here, 0. When x is 0, it's a lot easier to solve. So let's go ahead and plug into the graph. Y is equal to the absolute value of 3 times 0 plus 12, which is equal to the absolute value of 12, which is equal to 12. So when x is 0, y is 12. Let's go ahead and make the y scale 2. So 2, 4, 6, 8, 10, 12. So this is a point on the graph, 0, 12. Alright, let's plug in a value on this side of the graph and see what it is. Let's just go ahead and plug in this one. This is negative 5. So we're going to plug in x equals negative 5 now and see what we get. So let's plug in negative 5 here. Negative 5. So y is equal to the absolute value of 3 times negative 5 plus 12. 3 times negative 5 is negative 15. Negative 15 plus 12 is negative 3. The absolute value of negative 3 is 3. So when x equals negative 5, y equals 3. So that's here. Because this scale is 2. So it's halfway up there. Alright, let's go ahead and graph this now. Let's graph a line on either side. I wonder if this is what I'm looking for. Yeah, roughly. Okay, so it goes through this point. I'm going to adjust it to where, yeah, close enough. Okay, now let's do it again. And go from here through that point. So I didn't do a very good job drawing that. For some reason my line tools aren't working very nicely together. But that's roughly what it looks like. So let me show you a little trick. I didn't actually need to find this point here. And the reason why is an absolute value function is always perfectly symmetric. So I'm going to draw it in black so I see if I can draw a little bit nicer. Nope, I can't draw it any nicer by hand. It's always a perfectly symmetric V. Okay? And so if we have a value, a point here on the graph, if we go across, this is called the line of symmetry. Okay, it looks the exact same on either side. This is kind of like a mirror. If we go across that, we have the point. So here, this point is 1, 2 away from the line of symmetry. So if I go 1, 2 more, I have another point on the graph. So what does this mean? It means after I figured out, let me erase this. It means after I figured out the point 0, 12, 1, 2, 3, 4, 5, 6, 0, 12, I could have just come over here to the line of symmetry, 1, 2, 3, 4, and gone 4 more, 1, 2, 3, 4, and there's another point on my graph. And then I could have drawn it through those 2 points. And that's my graph. Okay, let me take a break from talking about absolute value functions for just a second to talk about a piecewise function. Let me get a grid up here. Okay, let's say this is my x-axis, and I mean my y-axis, and this is my x-axis. Okay, what a piecewise function is it's saying you have 2 separate graphs. So I'll do an example. A piecewise function a lot of times uses a curly bracket to show that this is the same thing. I want you to graph them both. I'm going to graph the line y equals x, and then I'm going to graph the line y equals 2x plus 2 at different times. I'm going to graph this one when x, so actually I'll write it in white so I can write it. Running out of space. Let me just move this. Okay, piecewise function, I'll write it over here. Oh no, I switched to white. Y is equal to x when x is greater than 1. Okay? And then I'm going to graph y equals 2x plus 2 when x is less than or equal to 1. Okay? So this is my piecewise function right here. So when x is greater than 1, here's the point, 1, that I'm going to be looking at. When x is greater than 1, I'm going to graph y equals x. So I'm going to go ahead and graph y equals x. Y equals x is going to look like this. Okay, and then y equals 2x plus 2 looks like this, up 2 over 1, up 2 over 1, up 2 over 1. Okay, so it looks like this. Okay, but what a piecewise functions is you don't graph the entire thing. I don't graph y equals x for the whole time, and I don't graph y equals 2x plus 2 for the whole time. What I do is I only graph y equals x when x is greater than or equal to 1. So right here, x is 1. So anything below that, I'm going to need a smaller eraser. Anything below when x equals 1, I'm going to erase. I only graph it, and here I'm going to put an open circle, and that lets you know when x is not equal to 1, it's just when x is greater than 1 that I use this line, y equals x. Now this other line, y equals 2x plus 2, we're only going to graph that when x is less than or equal to 1. So this is kind of hard to see. Let me go ahead and erase it. That says when x is less than or equal to 1. So here at 1, I'm going to erase all this stuff up here. I only graph it, so this is when x is less than or equal to 1. When x is less than or equal to 1, that's a closed circle because when x equals 1, we use this graph. So this, what I've drawn right here, this crazy looking graph, is a piecewise function. And that's going to be really useful for graphing absolute value functions. Let's do that now. Okay, so an absolute value function, you can graph it by using two lines in a piecewise equation. So the first thing that you want to do, we're going to graph this, is you want to get the absolute value all by itself on one side of the equation. So we've done that now. We subtracted by 5 on both sides, and we came up with this equation. The next thing that you want to do is remove the absolute value sign by writing a piecewise function. So remember, the definition of an absolute value is when x is when the stuff inside the absolute value is positive. So when x minus 3 is greater than or equal to 0, then the absolute value sign doesn't really do anything. So let's do an example of that. Y minus 5 equals the absolute value of, let's say, when x is 4 minus 3. Y minus 5 is equal to the absolute value of 1. So we have y minus 5 equals 1, so y equals 6. Okay. Now let's plug in 4 for x over here. Y minus 5 is equal to 4 minus 3. Y minus 5 is equal to 1, so y equals 6. It does the exact same thing because this step doesn't really do anything when the stuff that was inside is a positive number. So we write it like this. When the stuff that's inside, in this case x minus 3, this is what we're looking at here. When x minus 3 is a positive number or 0, then this graph and this graph are the exact same. But when x minus 3 is less than 0, we have the opposite over here. X minus 3, there we go. This is going to be the opposite. Let's look at an example of that up here. Let's plug in when x is equal to 0, for example. 0 minus 3, we're going to get a negative number here. Now we have y minus 5 is equal to the absolute value of negative 3. Now this absolute value does something. It does the same thing as if we were to multiply negative 3 by a negative 1. Y minus 5 is now equal to 3, so y equals 8. Okay, now let's plug in 0 for x here. Y minus 5 is equal to negative 0 minus 3. Y minus 5 is equal to negative 3. You see how on this step that negative number being multiplied does the same thing that the absolute value would have done. Y minus 5 is equal to 3. And then that gives us y equals 8. So this equation is the same thing as this equation if this stuff inside was a negative number. So what that means, in order to write an absolute value equation without writing the absolute value sign, to write it as two lines, you have to use a piecewise function. You have to write it like this: when x minus 3 is greater than or equal to 0, and when x minus 3 is less than 0. We have two separate cases. It's the opposite of this. Alright, so now we have two lines and a special case of when you graph them. I'm going to go ahead and write these lines, since we're going to graph them, I'm going to go ahead and write them in slope-intercept form. So this first graph in slope-intercept form, if I added 5 to both sides, plus 5, I would get y is equal to x plus 2. And then if I do that with this one, first thing is I need to, well, let me go ahead and erase this. I'll come back to that. So here I need to distribute. Y minus 5 is equal to negative x plus 3. I distribute the negative to both terms. Now I add 5 to both sides, and I get y equals negative x plus 8. So here's my other graph, and I'll rewrite the first one now. Oh no, having technical difficulties. There we go. Okay, so here was that first graph, x plus 2. So this becomes this, and this becomes this when you solve them. Alright, now when x minus 3 is greater than 0, if I added 3 to both sides, so if I said solve this for x, okay, then you would add 3 to both sides, and you would get x is greater than or equal to 3. These are the same statement. So I'm going to write when x is greater than 3, because that's easier for me to think about than when x minus 3 is greater than 0. And then if I do the same thing with the other one, if I add 3 to both sides, I get when x is less than 0. So here are my two equations. Let me erase these arrows so that it's not confusing. And the other original equations. There we go. So y equals x plus 2 when x is greater than or equal to 3, and y equals negative x plus 8 when x is, oh my goodness, less than 3. Made a mistake there. So here are our two equations that we're going to graph. This value 3, well, when x is 3, if I plugged in 3 here, that would make this, the stuff inside the absolute value, 0. If I plug in any number for x that's less than 3, I'm going to have a negative number in here. If I plug in any number for x that's greater than or equal to 3, then I'll have 0 or a positive number. So the absolute value won't do anything. So what we found is we found the x value, the point that when we plug something in, whether or not the absolute value, the sign changes. Alright, let's go ahead and graph those two lines. Here are our lines, y equals x plus 2 when x is greater than or equal to 3, and y equals negative x plus 8 when x is less than 3. Remember, an absolute value graph should look like a V, so that's what we should have. Okay, let's graph this line, x plus 2, it goes up 1 over 1, up 1 over 1. Okay, 1, 2, 3. Oh well. Alright, so here's my graph for this line. But remember, we only graph it when x is greater than or equal to 3. So I need to erase all of it up until here, because that's the point when x is 1, 2, 3. So the graph of this goes that way and it keeps going forever. Okay, now let's graph y equals negative x plus 8 when x is less than 3. 1, 2, 3, 4, 5, 6, 7, 8. So here's 1 point. But let's just go ahead and plug in. When x is 3, what would this graph be? It would be negative 3 plus 8, which would be 5. 1, 2, 3, 4, 5. It's going to start at the same point, just with an open circle, and then its slope is negative, so it goes this way. Let's plug in this point to check and make sure that's true. This point is 1, 2, 1, 2, 3, 4, 5, 6. So we need to plug in the point 2, 6 and make sure it's part of this graph. So 6 is equal to negative 2 plus 8. Is that true? 6 equals negative 2 plus 8? Yes, it's true. So this is what it looks like. It's a V. So the graph of these two inequalities is the exact same as the graph of this absolute value function, and that's a piecewise function. We're going to do quite a bit with piecewise functions, so you'll want to get used to those. Okay, the next thing that we're going to do is talk about real-world connections, so a way that you might see an absolute value graph. An absolute value is something that you often see with distance, where you don't really care where you are in relation to something, whether it's like a negative or a positive side. And that's often true in the real world. So here's an example. Let's draw a little house right here. This is Betsy Ross's house. And it's halfway on my way to school. So let's say my house is right here. And then the school, 1, 2, 3, 4, 5, 6. 1, 2, 3. This is the school. I'll draw 2 roofs because it's like a lot bigger. Okay, suppose you pass Betsy Ross's house. You walk at a rate of 1 city block per minute. Sketch a graph of your trip to school based on your distance and time from Betsy Ross's house. So this is actually, these shouldn't be houses, these should be times. Sorry about that. This will be the time that I pass Betsy Ross's house. But let's say at 1, 2, 3, 4, 5, 6, at negative 6 minutes, I'm at my house. Okay, it takes me 6 minutes. 1, 2, 3, 4, 5, 6. So over here, and these are blocks. So 6 blocks. So this is blocks, and this is minutes. So when I start off at my house, I am 6 city blocks away from Betsy's house, and I'm 6 minutes away because I walk 1 block per minute. So when I'm 5 minutes away, I've walked 1 block. 4, I've walked 1 block. 3, I've walked 1 block. 2, 1. When I've walked for 6 minutes, I'm at Betsy Ross's house. So my distance from her house is 0. My distance decreases from her house every time that I walk. So I'm walking this direction. Okay? And then as I start to walk past her house to school, I get farther away. So at 7 minutes, I'm past her house. I'm going towards school. At 8 minutes, I'm here. 9, 10, 11, 12 minutes, I'm at school. So this would be the graph of the distance, the number of blocks from Betsy's house versus the number of minutes that I walked. So here I was 6 blocks away, then 5, 4, 3, 2, 1, 0, I was passing her house, and then 1, 2, 3, 4, 5, 6 blocks away when I got to school. This would be the graph, an absolute value function. Okay, and that's it for this section.